Welcome to Lecture 7. The material that we're going to begin discussing in this lecture comes from Units 3 and 4. The first concept I want to talk about, or two concepts actually, minterms and max terms. And we'll talk about minterms first. Suppose that we have a function of the Boolean variables x, y, and z. And suppose that this function is defined in the following way. Let's say maybe we have x prime y, or yz, or x prime y z prime, or maybe we might have x, or x y prime z prime as an example. Now you might look at this and perhaps there would be some ways to simplify this, but that doesn't matter. The main point is that this is our function of our function f, and again our three independent Boolean variables are x, y, and z. And if we look at this expression, this term x prime y z prime, and likewise this term x, y prime, z prime, are called minterms. But none of the other three terms, x prime y, or yz, or x, none of those is a minterm. So what is a minterm? A minterm is the product of all the Boolean, I'll say all the available Boolean variables and perhaps I'll say is the simple product of all the available Boolean variables in either complemented or uncomplemented form. And so you can see, once you see that definition, you can understand why the first two terms are not minterms. X prime y is not a minterm because it doesn't involve z, and z is one of the Boolean variables available. Yz is not a minterm because it doesn't contain x, and over here x alone does not contain y or z. So that's why those three terms are not minterms, and yet you can see readily x prime y z prime. It is a simple product of all the available Boolean variables in either complemented or uncomplimented form, so this is a minterm. And x y prime z prime likewise involves it is a simple product of all the available Boolean variables in complemented or uncomplimented form, so this is also a minterm. Let's look at another example. If we had g of x, y is equal to x or y, y prime, or x, y prime, or x, in this case, this would be the only minterm. The xy prime term is the only minterm, and the rest of this, the other two terms, are not minterms. Now, to explain that, the reason that this first term is not a minterm is that it is not a simple product. It isn't simply the product of Boolean variables, but it is a product of a Boolean variable with a sum of Boolean variables. So that's why that's not a minterm. And the last term is not a minterm because it doesn't contain either y or y prime. And notice another interesting thing here is that here in the previous problem, x prime y is not a minterm, but here in this problem, x y prime is a minterm, and you might be confused by that. Of course, the reason is that in the previous problem we had 3 Boolean variables available, and so for x prime y to have been a minterm, it would have had z or z prime involved. But down here, this g function that we're talking about is only a function of 2 Boolean variables, so a minterm here will be the product of only 2 variables rather than the product of 3 variables, as was the case up here with f. So to just stress that idea, if somebody asks you, is wxy prime a minterm, if somebody asks you that, you cannot answer that question until you know what Boolean variables are available. If wx and y prime, if it's a problem like this, f of wxy is equal to wxy prime plus some other terms, then in that case, wxy prime is a minterm. But in a problem, if you had g of w, x, y, and z is equal to wx, y prime plus some other terms, then in this case, wx, y prime is not a minterm. So in order to say whether or not something is a minterm, or for that matter a max term, we haven't talked about those yet, but in either case, you need to know what are all of the Boolean variables that are under consideration in the problem at hand. Now, let's go back to our, well, let's just maybe make another example. Let's say, for instance, we might say f of x, y, and z is equal to x, y, or x, y prime, z prime. Here's an example, and I hope that you will all readily agree that this second term here is a minterm because it is a simple product of all of the Boolean variables under consideration, and this first term is not a minterm. Now, you might be curious to know where this terminology minterm comes from, and I can show you that very easily by looking at the truth table for each of these terms. So, in this problem, we have x, y, and z are the possible Boolean variables, and then we'll look at the truth table for x, y, and then over here we'll make a truth table for the term x, y prime, z prime. And let's see what these two truth tables look like, and then we'll be able to see why x, y prime, z prime is a minterm, or why it's called a minterm, and why x, y is not. Now, as usual, we want to consider all the possible combinations of the Boolean variables. And we always will list them in this order. When there are 3 Boolean variables and they're listed in our function in the order x, y, and z, then we'll list them in that same order in the truth table. And then when we list out the different possible combinations, notice we list them in such a fashion that if we considered each threesome to be a binary number, then we would have 0, 1, 2, 3, 4, 5, 6, and 7. So it's important to realize that we always will list it in this way. Now, if we go ahead then and evaluate x, y for each one of those possibilities, we can easily very quickly fill in the first 4 rows, because in each of the first 4 rows, x is equal to 0, and 0 ended with anything is 0. So we know for sure that x, y is equal to 0 in the first 4 rows. Similarly, x, y is equal to 0 in the next 2 rows as well, because in those 2 rows, y is 0. And again, 0 ended with anything is 0. But in the last 2 rows, x and y are both equal to 1, and 1 ended with 1 is 1. So for the last 2 rows, x, y is equal to 1. And so this would be the truth table for the term x, y. Now let's find the truth table for the term x, y prime, z prime. Okay. We can, once again, as we did before, we can say immediately the first 4 rows will be 0, because we noticed that in this term x, y prime, z prime, the first variable is x, and x is equal to 0 in the first 4 rows, and 0 ended with anything is 0. So we immediately get 4 zeros. Now the next term is y prime, and y prime will be equal to 0 whenever y is equal to 1. And so if we look at our remaining rows, we see that here, looking at the y column, we can see that y is equal to 1 in each of the last 2 rows. So if y is equal to 1, again, then this will make y prime equal to 0 up here in this expression. But if y prime is equal to 0, then we have x ended with 0, ended with z prime, and 0 ended with anything is 0. So we can immediately put a 0 in the last 2 rows. And now all we have remaining to consider are the combinations 1, 0, 0 and 1, 0, 1. Well, when x is equal to 1, and y is equal to 0, and z is equal to 0, well, since x is equal to 1, we'd have a 1 here for x. Y prime, since y is 0, y prime will be 1. Since z is 0, z prime will be 1. So this would give us 1, ended with 1, ended with 1, which is 1. And for this final term, 1, 0, 1, well, notice that when z is equal to 1, this z prime here in this term x, y prime, z prime will be equal to 0. And 0 ended with anything is 0. So this is the truth table for the term x, y prime, z prime. And the difference that we notice when we look at these two truth tables is that the truth table for x, y prime, z prime, which is a minterm, yields a value of 1 under only one circumstance. But when we have this other term, it yields a value of 1 under more than one circumstance. I don't want to say exactly, I mean, in this case it's 1, but for instance, if we had looked at, let's look, so let me, actually I'll say this is not a minterm. And as another example, we could do something like this. If we said x, y, z, and let's say another example of something that's not a minterm would be x prime. And so if we drew up the truth table for that, we readily see that x prime, is very easy to get the truth table for that because x is equal to 0 in the first 4 rows, so therefore x prime is 1. And in the last 4 rows, x is 1, so x prime is 0. And so this too, this function as well, or this term, is clearly not a minterm because it is equal to 1 in a number of different cases. But a 1 is, a minterm is equal to 1 on a minimum number of occasions, which is just one occasion. There's only one combination of the variables. In this case, for this minterm, it would be 1, 0, 0. Only that combination of the variables will make this term equal to 1. All other combinations will make it equal to 0. So that's the idea of why a minterm is called a minterm, is because it's equal to 1 in a minimum number of situations. Now this idea is actually very powerful, and in fact it relates to the final problem that you had on quiz, on test 6. Let me remind you of that problem, or to be honest, I don't remember the exact numbers, but I can give you an example similar to it. So I'll say example similar to the final problem on test 6. Now you will remember that on that final problem we had something like this. We had a truth table, x, y, z, and then we had a function f of x, y, z. And so you had a truth table, and this was filled in. I believe the numbers might have been this 0. No, maybe it was, well, I think it was 0, 1, 1, 0, 0, 1, 0, 0, something like that. It doesn't matter. The example is, the idea is the main point. So suppose that we had this function f of x, y, z, and this is a truth table for f. And we want to express f in terms of x, y, and z. Well, so I'll say express f of x, y, z in terms of x, y, and z. Okay, that's our goal. Well, I'm going to do something called using the Minterm expansion. So one way to do this is to find the Minterm expansion for f. Now, what does this mean? Well, let me just go ahead and give you the answer, and then we'll see why it's true. And actually, what I'll do, I'll go ahead and put the answer up here, and then I'll transfer it down to the bottom of the page in a moment. The Minterm expansion for this function f of x, y, z is the following. I'll go ahead and write down the answer, and then I'll explain why it's true. Okay, that is an expansion of the function f in terms of minterms, which is also called a Minterm expansion. And let's now try to understand this expression. Well, first of all, I hope that all of you will agree that each one of these three terms is indeed a minterm, because each one is a simple product of all of the available Boolean variables in either complemented or uncomplemented form. So it's clear that all of these are minterms, but how can we see that the sum of these three minterms is equal to this function f that's shown over here in the truth table? Well, think about what we just learned. Remember that each one of these minterms is only going to be equal to 1 in one case. In other words, under one possible combination of the variables x, y, and z. So let's identify those combinations, and I think that that will help us to see that this expression is indeed equal to the given function f. Let's first look at x prime, y prime, z. What combination of x, y, and z will make this minterm equal to 1? Well, if any one of these variables here is equal to 0, it certainly can't be equal to 1, because 0 ANDed with anything will give us 0. So we have to choose x, y, and z in such a way that each one of these will give us 1. Well, for x prime to be equal to 1, x must be 0. For y prime to be 1, y must be 0. And for z to be 1, well, z must be 1. So the combination that will make the first minterm equal to 1 is x equals 0, y equals 0, and z equals 1. Now, I suggest that you turn off the tape for a moment and try to find the situations that will make the remaining two minterms equal to 1, and then resume. Okay, I hope that you concluded that for this second minterm, the situation that will make it equal to 1 is x equals 0, y equals 1, z equals 0. We need x to be 0 because we have an x prime here, and we need z to be 0 because we have z prime. Y is just itself. So when x is equal to 0, that will make x prime 1. When y is equal to 1, then of course y is 1. And when z is equal to 0, z prime will be 1. So we have 1 ANDed with 1, ANDed with 1, which is 1. And finally now, what are the circumstances, or what is the combination of variables that will make the last minterm equal to 1? Well, we want x equal to 1, y equal to 0, and z equal to 1. Now, let's think about, to finish our line of reasoning here, let's think in the following way. Okay, so the first minterm, the x prime, y prime, z term, will always be equal to 0, except when x is 0, y is 0, and z is 1. The second term will always be 0, except when x is 0, y is 1, and z is 0. And the last term will always be equal to 0, except when x is 1, and y is 0, and z is 1. So when we sum these things up, when we sum up these three terms, well, obviously if we're summing up 0 ORed with 0, ORed with 0, we're going to get 0. So f will always be 0, except when one of these minterms is equal to 1. So f will be 0 in all situations, except it won't be 0 when x is 0 and y is 0 and z is 1, because in that case the first minterm is 1 and 1. Now, true, this minterm and that minterm, the second minterm and the third minterm, are still equal to 0 under that choice of variables, but the first one is now, when x is 0, y is 0, z is 1, the first minterm will be 1, and 1 ORed with 0, ORed with 0 is 1. So in this combination, x is 0, y is 0, z is 1. That's one time when f will be 1. Likewise, when x is 0, y is 1, and z is 0, the first minterm and the last minterm will be 0, but this one will be 1. And so 0 ORed with 1, ORed with 0 is 1. And finally, when x is 1, and y is 0, and z is 1, this minterm will be equal to 1. The first two will be 0. And so we'll have 0 ORed with 0, ORed with 1, which is 1. So there will be three cases when f is equal to 1, and in all other cases it will be equal to 0. In the three cases when f be equal to 1 are x equals 0, y equals 0, z equals 1, x equals 0, y equals 1, z equals 0, and x equals 1, y equals 0, z equals 1. And if you look now at the truth table, you will see that exactly, the description we just gave, exactly matches the information in the truth table. We see that f is always equal to 0, except the first case when it's not equal to 0 is when x is 0, y is 0, and z is 1, which of course is this case. The second case when f is not equal to 0 is when x is 0, y is 1, and z is 0, which of course is the second case. And the final situation that will make f not equal to 0 is when x is 1, y is 0, and z is 1, and that's this case. So you can see how I was able to come up with this minterm expansion so easily. I simply looked for the rows here, these three rows that contained ones, and then thought about what the corresponding minterm would be. And that's how we find the minterm expansion for a function. So let's repeat down here this minterm. We have x prime, y prime z, or x prime y z prime, or x y prime z. Now, again, this is the minterm expansion. For f. Now, sometimes we use another notation, And that notation can be explained in the following way. It's convenient, especially when you have many Boolean variables available. It's convenient to find a shorthand way of noting the minterms rather than having to write out every single variable as we have here. Notice we have x, y, z, x, y, z, x, y, z. We just have to note which ones get the primes and which ones don't. Well, when you have maybe 6 Boolean variables, it gets tiresome to write out all 6 variables again and again and again, simply so that you can then put complements in some locations. So what is this alternative notation? Well, it goes in the following way. You want to know the situation. We already know that the minterm will equal 1 in only one situation, and so we use that situation to actually name the minterm. Let me show you what I mean. So if we look at this first minterm here, x prime, y prime, z, as we have already noted, that will always be equal to 0, except in the case when x is 0, y is 0, and z is 1. Now we interpret those three numbers together as a binary number, and the binary number, of course, 0, 0, 1 would be the binary number 1, and so we say little m. That's because of minterm. Minterms will get a little m, and later when we get to max terms, that will get a capital M. But this is little m and then the number 1. The next minterm here will be equal to 1 when x is 0, y is 1, and z is 0. And the binary number 0, 1, 0 is the same thing as 2. So this is M2. Now take a moment to try to figure out the notation for the last minterm, and then we'll do it together. Okay, I hope you concluded that for this one, we need x equals 1, y equals 0, and z equals 1. And so this 1, 0, 1, the binary number 1, 0, 1 is 5. And so we have little m5 for that. And we can also look up here at the truth table. We see this is 0, 1, 2, 3, 4, 5, 6, and 7. And sure enough, in the rows 1, 2, and 5, those were the rows that had 1s. So this is an alternative notation for f, and still another way, an even more compact way of listing this is the following. We say summation of little m 1, 2, 5. So these are just different ways of identifying the function f and expressing it in terms of minterms, which is a very handy thing to do. Let's now look at another example just to emphasize how convenient this idea of a minterm expansion can be. Suppose in this example that we have the following. G of xyz is equal to xyz prime, or x prime, y prime, z prime, or xyz. Now, I hope you recognize that each one of these is a minterm. And suppose that we were asked to find the truth table for G. Well, I hope that you're now ready to do this rather quickly. Remember, as usual, we'll list on the left the independent variables, which in this case are x, y, and z. But now we're not going to have any intermediate columns at all. We won't need those because of what we've learned about minterms. We'll be able to write down g of x, y, z immediately. And let's see how this goes. Now, so those are all the possibilities for x, y, and z. Those are all 8 possible combinations. And now, as I mentioned, because of the power of this minterm expansion idea, we're not going to have to list any intermediate columns at all. We'll be able to immediately write down what g is equal to, and the way that our reasoning proceeds is as follows. We notice that if we think about each one of these minterms individually, we see that the first one will be equal to 1 only when x is 1 and y is 1 and z is 0. The second one will be 1 only when x is 0, y is 0, and z is 0. And the last minterm will be 1 only when x is 1, y is 1, and z is 1. So these 3 combinations, 1, 1, 0, 0, 0, 0, and 1, 1, 1, are the only 3 situations in which this function will be equal to 1. In all other cases, each one of the minterms will be 0, and if each one of those is 0, then on the right hand side we have 0, ORed with 0, ORed with 0, which of course is 0. So we come over here to the table, and for the first one we write 1 because that's the 0, 0, 0 option, and we're going to also have 1 in the 1, 1, 0 position because of the first minterm, and a 1 in the 1, 1, 1 row because of the last minterm, and everything else will get a 0. And that we have the truth table for g just that quickly. And if we were challenged to write the expression for g in this alternative notation that we learned, we could write the following. We can say g of x, y, z is equal to, usually we write these in ascending order, so we would write little m 0, ORed with little m 6, ORed with little m 7. Notice that little m 0 is this middle minterm, the 0, 0, 0 one. M6, 6 of course is 1, 1, 0 in binary, and then 1, 1, 1 in binary is 7. So M0 is the middle minterm here, M6 is the first one, M7 is the last one. Or we could also write this even more compactly in this way. So that's how we would do a problem like that. So now that we see the power of this minterm idea, we can readily see why it's an attractive thing to do. And so it might occur to you, well, suppose you have an expression such as this, f of x, y, z is equal to maybe x prime y or y prime z. And you wanted to find the truth table for that. Well, notice right away that we cannot use the ideas that we've just been developing for minterm expansions because neither one of these terms on the right hand side is a minterm. And so this looks like a situation where we'll have to list the independent variables on the left hand side and then have some intermediate columns where we would calculate x prime y and then y prime z, and then finally have a result column where we OR those two together. That looks like the case. But actually, there is another alternative. We can convert this, we can take the approach of first converting this to a minterm expansion. So we'll say, first get a minterm expansion. Now, you might wonder, how do we get a minterm expansion when neither of these terms on the right-hand side is a minterm? Well, it can be done in the following way. Okay, we'll rewrite our function f of x, y, z is equal to x prime y. Now, remember that anything ANDed with 1 is equal to itself. So we're going to AND that term with 1. And likewise, we will AND the second term with 1 as well. And I notice that I'm putting 1 in the location of the missing variable. In other words, in this first term, what's missing, what we would need to make it a minterm is something in the z position. So here I've put a 1 in the z position, and in the last term I've put a 1 in the x position because we don't have anything there in the second term. Now I'm going to pull the following trick. We know that one way we could rewrite the number 1 is as this: z ORed with z complement. Any Boolean variable ORed with its complement will be equal to 1. For instance, when z is equal to 0, z prime is 1, and when z prime is 0, z is 1. So always one or the other of these two terms will be 1, and 1 ORed with anything is 1. And we do the same thing in the second term, except this time we rewrite 1 as x or x prime. And now if we multiply this out, we get x prime y z, or x prime y z prime, or x y prime z, or x prime y prime z. And now we have a minterm expansion, just that easily. And to actually get the truth table, probably the very easiest way is to go to the alternative notation. So we do that by remembering that, okay, the first one is going to go to 1 when x is 0, y is 1, z is 1. The second one will go to 1 when x is 0, y is 1, and z is 0. The third one when x is 1, y is 0, and z is 1. And the final one when x is 0, y is 0, and z is 1. So if we think about these numbers, this is the number 3, this is 2, this is 5, and this is 1. So f the function f is the same as the summation of the four minterms m1, m2, m3, and m5. And so now that we have found the minterm expression for f, we can easily get the truth table So we have minterm 1, 2, 3, and 5, and therefore we put a 1 in the rows corresponding to the binary numbers 1, 2, 3, and 5, and all the other rows will get 0, and that is it. That's the truth table for f. And the final point I want to make in this lecture, let's do one final example, and then we'll look at some test problems. But let's, in this final example, let's suppose that g of x, y, z were equal to x or y prime, and let's just say that we were asked to find the minterm expansion. Well, clearly neither one of the terms on the right hand side is equal to a minterm. In fact, neither one is even very close, because the first term is missing y and z, the second term is missing x and z, and so we just extend the idea that we employed in the previous example. We write down 1 wherever we're missing a variable, so that becomes x and 1 for that first term, and 1 or y prime or 1 for the second term. And now we will proceed as follows. This first one here we will rewrite as y or y prime, and the second one we will rewrite as z or z prime. And for the second term, we will have x or x prime, y prime, z or z prime. And so now, if we complete this, we will have xyz or xyz prime, or x y prime z, or x y prime z prime, or x y prime z, or x y prime z prime, or x prime y prime z, or x prime y prime z prime. Okay, just checking the work here, and I believe everything is correct. And now let's go ahead and put this into the so-called little m notation. So we'll have 111 there, 110. No, remember now, I'm just writing down the values of that the variables would need to have in order for the minterm to be equal to 1. So 111 and 110. Here we would need 101. Here 100, 101, 100, 001, and 000. And of course 111 is 7, 110 is 6, 101 is 5, 100 is 4, 101 is 5, 100 is 4, 001 is 1, and 000 is 0. Now, before we proceed to the final step, notice that we have some repetition here. We have little m4 here, x prime, y prime, x, y prime, z prime, and we have the same term here, x, y prime, z prime. Well, we know that any Boolean expression ORed with itself is itself, and so we can take one of those away. And likewise, we have little m5 repeated. X, y prime, z is here, and x, y prime, z is also over here. So we can take away that as well. And once we've taken those two away, there are no repetitions, and so we'll write down our final result. I think I'll leave a little more space here. And we have g of x, y, z is equal to the sum of the minterms 0, 1, 4, 5, 6, and 7. And there is your minterm expansion for G. And now, of course, you know that it would be very easy to find the truth table for G. So that shows the power of the idea of minterm expansions. And now we'll have a test on that idea, and then for the next lecture we'll talk about max terms and max term expansions. So our two test problems are the following. 7.1 says, which of the following is a valid expression for the function represented in this truth table? So we have a function f of the three Boolean variables x, y, and z, and there you have the truth table for f, and then you're given 4 possible expressions for f, and you need to choose which one of these is a valid expression for f. And then for problem 2, you're asked to find the minterm expansion for the function g of x, y, z, which is equal to x complement ORed with y and z. And you have 4 expressions there, a, b, c, and d, given in the little m notation, and you need to find which of these is the correct minterm expansion for the function g. Good luck, and that concludes lecture 7.